I was asked yesterday a very interesting question by one of you. Somebody knew that transformers are used to, in power lines. When we transmit electricity from power station to a city, we use actually transformers at the power station to increase potential difference between the wires which we use to deliver electricity to a town or on a city, and then we use a step-down transformer to reduce this potential difference so that we can use it in our households. And well, this procedure actually saves energy, quite a lot of this of energy, because now think what, let's say that we have a town somewhere over here, and power station there, and deliver electricity. Well, the amount of energy which is delivered to a city is equal to the product, this is power. In other words, amount of energy delivered in unit of time is equal to the product of potential difference over here and the current over there, and current flowing in the wires. All right, so now let's say that we have two situations. In one situation, potential difference between the two wires which deliver electricity is 100 times greater than than potential difference at another time, which means that how much more current do we need to run in both situations? Compare the currents in both situations. One that potential difference is relatively low, and the other one that potential difference is 100 times more. So what can you say about the currents, assuming that the same amount of energy has to be delivered to the city? Well, power delivered to the city is equal to root mean square value of the current times root mean square value of the potential difference. Now, if we want to deliver certain amount of power, let's say 1 megawatt, and we play with potential difference between the two wires. In one case, we have potential difference 100 times greater than in the other. What can you say about the currents? We're saying, Adam? We say? 1/100th, correct. When you increase potential difference between the wires, you can decrease the current flowing in the wires 100 times. Right now, let's see how much energy actually, because wire is a resistor, right? So this wire has a certain resistance. It means that there is also power dissipated in this wire. Now, what is it used for? Power dissipated in the wire. It's wasted. It never reaches the city. It's wasted. It just heats up the atmosphere on the way from the power station to the city. All right. Now think about in which case power dissipated in the wire is greater, when the current is small or when the current is large. Well, it's again actually the same formula. This time, however, we would have to take potential difference between this point and this point for one wire, and potential difference between this point and this point. Now, if a wire, since wire is like a resistor, it obeys Ohm's law, so this power wasted is equal to, well, current flowing in the wire multiplied by potential difference between the ends of the wire, root mean square values, and in a resistor, potential difference is proportional to the current. So actually I can write down that this is square of the root mean square value multiplied by resistance of the wire, which is used to deliver power from power station to the city. So when we increase potential difference between the wires 100 times, current drops 100 times. How many times power wasted drops? Well, current drops 100 times. Here we have to square it, which means 10,000 times less energy is wasted. Well, I mean, would be wasted in the wires delivering electricity to the town if at the power station we increase potential difference between the wires. And this is the reason we are doing it. Now we have also limitations, because I mean the obviously the higher potential difference, the less energy is wasted. But we don't have technology then to prevent dielectric breakdown of the air. So we would have to build the poles and higher and separate the wires more and more and more. So we have to figure out where is the balance between the cost of building power line and what potential difference we use. All right. So after this digression, I can come back to the lecture and in today's lecture, we are getting into new subject. This won't be on the test. We are getting now into optics. And the first subject which I want to talk about, what optics is about. It is about radiation. How radiation is transferred, what tricks we can do with radiation. And let me remind you that we heard about radiation already in Physics 1. I mentioned at the time that it is one of the ways we transfer heat. Heat can be transferred 3 different ways. One is by convection, when mass of fluid moves from one location to another location, heats up that this vicinity. Second mechanism was conduction. So if you have a rod, for example, and heat one end of the rod, you will feel warmth after a while at the other end of the rod. And the third mechanism was radiation. Now, the first 2 require a substance for transfer of heat. Radiation doesn't. I mean, it depends actually how we treat radiation. But in principle, we are getting radiation coming out from the sun to the earth, and actually it's quite a lot of energy. I heard, I know about certain statistics that if we were able to convert or to harvest the power coming from the sun to the earth, just on the surface of the earth, that amount would be 5,000 times greater than the current consumption of energy on earth, which is actually well, because of that, you probably heard about alternative sources of energy, and one of the hot topics in research is to harvest this energy, to make solar batteries and grab that energy and convert it to, well, whatever we want to do. All right, word radiation actually has double meaning. One is that it is the process in which energy is emitted in form of waves or particles. So you can think about radiation, and actually radiation has a proper so-called property of duality. Every radiation behaves simultaneously like a beam of particles or a wave. In some circumstances, one nature takes over and manifests itself more than the other. In this course, we will limit ourselves actually only to the well, mainly to the wave nature of radiation. Also, energy radiated in the form of waves of particles is also called radiation. So, for example, if we think about the sun and the sunlight which falls on the earth, we can say that it is radiation. Which one? A or B? B, correct. This is B. We are talking about the energy which was delivered to the earth. Now let me try to phrase another. Actually, we are getting this radiation due to sun's radiation. I mean, over here, actually, I probably one can interpret it both ways, but the second phrase is more like an A version of the word radiation. Now, we will limit ourselves actually only, I mean, in this course, only to one type of radiation, which is associated with, I mean, if we look at the waves, it is associated with electromagnetic waves. In electromagnetic radiation, both electric field and magnetic field oscillate at each point along which this radiation travels. And as I mentioned, every radiation exhibits dual nature. If we consider electromagnetic radiation as a beam of particles, these particles are called photons. And photons actually are concept, or as humanity, we thought first about radiation that it is a beam of particles. Newton recognized radiation as a beam of particles. It is later on, in 19th century, actually we discovered wave-like nature of radiation. And then we switched to another understanding of radiation and recognized that it's a wave. And in 20th century, we came to the conclusion that actually some of the phenomena cannot be explained based on the wave nature of radiation. That really thinking about radiation as a beam of particles made more sense. So then we came back, then we introduced that concept of duality. Now, in electromagnetic radiation, both electric and magnetic field oscillate. So if I try to draw electromagnetic wave, this is how it is going to look like. We'll have oscillations of electric field and of magnetic field. And electric field will be always, I mean, we'll see in a moment, that electric field always has to be perpendicular to the magnetic field, and the two actually the orientation of the two is related to the direction of propagation of radiation by right-hand rule. So vector product of electric field and magnetic field actually says which way the wave will travel. So for example, this wave will travel from the sun, well, toward the earth, not the other way. Yeah, because if you freeze a wave, you don't know which way it travels. All right. Now I'll show you something what will really surprise you, because I said that we are beginning a new chapter, optics, but it is based on Maxwell's equations. Yeah, so all right, let's consider relationship between electric and magnetic field based on Maxwell's equations. So I consider here a differential loop. So each of the sides of this rectangle, you can even think that it is a tiny square, is differential. And let's say that we have electric field in this direction. Well, Maxwell's equation, one of the Maxwell's equations, so it is Faraday's law of induction. I will now calculate at what rate, because this electric field is related to the rate of change in magnetic flux through that surface, which means that I have to consider a magnetic field which is perpendicular to that plane. If I consider electric field in this direction, so I can calculate line integral, and I will have a non-zero line integral along this contour. I would have to consider magnetic field perpendicular. Only that perpendicular magnetic field induces electric field. And let me remind you that the line integral of electric field along this loop is proportional to the rate of change of magnetic flux. So now I'm evaluating this magnetic flux and rate of change. In other words, I have to calculate derivative of the flux with respect to time. Well, it's a tiny rectangle with dimensions dx and dy, so the area of this piece is dx times dy. If I multiply it by magnetic field strength, then I have flux. So I have to calculate the derivative of this expression over this loop. Now, if I consider this loop, dx and dy are time independent, which means that the rate of change of magnetic flux through this loop is proportional to the rate of change in the magnetic field multiplied by the area of this flux. All right. Now, this rate of change of magnetic flux, according to Faraday's law of induction, which is the third Maxwell's equation, is proportional to the line integral of electric field vector. So now I will evaluate electric field and relate it to the dimensions of that rectangle. Well, I have just 4 differential pieces. Over here, over here, over here, and over there. All right, so now where did I start? I started, let's say that this point is x, so this point is x plus dx. So I have to take electric field at this location and multiply by the differential segment vector times cosine of the angle between the segment vector and the electric field vector. It happens to be angle is 0, so cosine of 0 is 1. So this first term is a contribution to the line integral along this side of that rectangle. Now let's think about this side. Well, it's 0. Why? Because the segment vector is in this direction, electric field is up. So when I calculate scalar product, I have to take length of this segment, electric field strength, and cosine of 90 degrees. Cosine of 90 degrees is 0. All right, now I have this side. And well, it's similar to the other one, except that I have to take electric field at this location. So this electric field strength at this location, length of this segment, and where did I get that minus from? From the angle. Segment vector is down, electric field is up. So I have to take cosine of 180 degrees. It will give me this minus. All right, what did I do here? Oh, I just expanded this function into, Taylor series. So I can write down that this function is equal to the value of the function at x plus derivative of this function with respect to x multiplied by dx. And I take just the first two terms of the expansion. Now I see that this term and this term cancels, and I get I simplify this line integral to such an expression. Now this line integral is supposed to be equal to this rate of change in flux, which means that this expression must be equal to this expression, right? Now here I have dx and dy, and here I have dx and dy, which so the conclusion is that from Faraday's law of induction, I relate electric field with magnetic field. Derivative of electric field with respect to position is opposite to the derivative of magnetic field in the direction perpendicular to that plane with respect to time. Well, I'm not going to go through the other analysis, but if I repeated a similar analysis using fourth of the Maxwell's equation, the Ampere-Maxwell law, I would also be able to relate magnetic field to electric field, but this time derivative of magnetic field with respect to position is proportional to the derivative of electric field with respect to time. The relations are almost symmetrical. Derivative with respect to position of one of the fields is proportional to the derivative with respect to time of the other field. Now I can combine those two equations together. Now how can I do it? Well, here I have derivative of a magnetic field with respect to time. Here I have derivative with respect to position. So if I calculate derivative of both sides here with respect to position and over here with respect to time, on the left, here I will have derivative of magnetic field with respect to position and time, and here I'm going to have derivative of magnetic field with respect to position and time, which means that after I combine those, and actually I'm doing this entire analysis here. So I started from this expression here. Second derivative with respect to position, well, requires that I take second derivative with respect of position of this derivative with respect to time. Now, fortunately, it is not true in calculus for any functions, but fortunately in physics the functions are relatively nice. So actually it doesn't matter in which order we calculate derivative of magnetic field. So I can write down that instead of having derivative with respect to time and then with respect to position, I can take first with respect to position and then with respect to time. The derivatives are interchangeable. Now why did I do that? Because now I can substitute this expression over here, and after simplification I get a differential equation just for the electric field. The second derivative of electric field with respect to position is proportional to second derivative of electric field with respect to time. And as humanity, we are able to solve it. Well, we can do the same thing the other way, starting with this expression and taking derivative with respect to position of both sides, and then substituting this expression, and we get relationship between magnetic fields. Well, you will learn how to solve these differential equations. Sometimes when you take differential equations, over here I will just give you the solution. So let's come back here. So these are the equations which we obtained for electric field and for the magnetic field. I copy these two equations. And let's look for solutions. Well, and it happens, actually it is that well, do you know a function? Well, no, maybe it isn't clear, because here is derivative with respect to time, and here's derivative with respect to position. These type of functions, trigonometric functions, satisfy these two equations. Now, this is a general form of a trigonometric function. Now we will have to adjust appropriately the constants in the function to make sure that this equation is satisfied. Not for every combination of constants. And where are the constants? The peak value of this of the electric field vector and the peak value of magnetic field. These are constants. We can adjust them. Now this constant k, which formally actually it represents magnitude of the propagation vector. Propagation vector actually says in which direction the wave moves and what is the wavelength of that wave, and angular frequency. Now, in the more general case, rather than having kx, so if you take an advanced course of electrodynamics, you will have a scalar product of indeed a vector and position vector rather than x component. We have already placed a constraint that our wave is traveling along x direction. So if the wave travels along x direction, then we have kx over here. The remaining two components of the propagation vector are 0. All right, let's now take a look at what conditions the constants have to satisfy in order for these two functions to satisfy the wave equation. So we can do it by direct substitution. So if on the left hand side, I calculate second derivative with respect to position of this expression. Well, first derivative of, recognize this is a composite function. Em is a constant. We can take it in front of derivative. First derivative of cosine is going to be minus sine, and then second derivative will require that we take derivative of this minus sine, so I will get minus cosine of this expression. So definitely I will have Em cosine of kx minus omega t. So after taking derivative, I still have the same function. However, when I calculate the derivative, I also have to take derivative of the internal function. It's a composite function. So when I take first derivative, I will get 1k, and second derivative, I will get again k. So this is where that k square came from. By taking second derivative of this function, I'm getting this function multiplied by minus k squared. This is what I have on the performing operation, after performing operation of the left-hand side of the equation. Now let's perform operation on the right-hand side of the equation. So I will have permeability of free space, permittivity of free space. And again, first derivative will give me minus sine And then second derivative will give me minus cosine, and so I will get back the function, and then I have to take second derivative of the internal function, which will give me this omega square. So this is how I got this omega square over here. Well, I can recognize now that the functions cancel on that side, and ratio of these two constants must be equal 1 over permittivity of free space and permeability of free space. Now what can I say about the peak value? It didn't matter. So this equation is satisfied by any function of this form with an arbitrary value of the peak value, and propagation vector and angular frequency have to satisfy such a condition. I can actually think about it that omega divided by k is 1 over square root of permittivity of free space multiplied by permeability of free space. And actually this quotient has a physical meaning. Let's think, I mean, if we take this function, let's say that I draw this. How about if I draw this function? How should I draw this function? Let's say that I consider this function at instant t equals 0. Well, at t equals 0, we just have em times cosine kx. So it's a cosine function. This a function looks like that. Right? Now, just a little bit later. So consider an instant that now this is not 0. Let's say that this is pi over 4. How to draw the function when omega t is equal pi over 4? Well, if the argument of cosine function is varied, it means that, in general actually, if we have a plot of function, how to draw a plot of function where argument is different by constant a. So if I have, for example, function f of x, how function f of x minus a looks like? It is shifted, correct? It is shifted to the right, but by how much? By a, correct. Yes, so I ask you to consider a situation that omega t is pi over 4, which means that the function is going to be shifted by pi over 4 to the right. Right? Now I will wait a little bit more of time, so that shift is pi over 2. What happens to the function? Well, it is shifted further. Yes, so as time passes by, this shape is moving to the right. The wave travels. And let's try to evaluate how fast it travels. And you will have to imagine that you are a surfer. So let's say that you jump on a certain face and stay over there. It means that as time passes by, you stay on a particular phase. Well, and I will now try to determine how fast you will have to move in order to stay there. Well, it means that you have to change x in such a way that this expression is constant, right? So kx kx minus omega t is equal to constant, which means that x is equal omega t plus constant divided by k. Well, let's calculate derivative of this function now. And derivative, well, k is a constant, I can take it in front. Derivative of omega t is omega, derivative of constant is 0, so I get that x component of velocity at which wave travels along x direction is equal to the angular frequency divided by the magnitude of the propagation vector. Well, we are talking about electromagnetic wave, which means that, if I plug in this expression over here, it is how fast electromagnetic waves travel through space. Now, one of an example of electromagnetic wave is the light, which means that the ratio of omega over k, which happens to be equal 1 over square root of permittivity of the product of permittivity and permeability, is the speed of light. We found that speed of light, and indeed, if you plug in permittivity of free space and permeability of free space, you will get speed of light, which you have on the cover of the book. Well, we can repeat the same. Oh no, actually, right now I want to show a relationship between electric and magnetic field in the electromagnetic wave. So actually, it's directly from one of the equations without combining the two equations, which were on the yellow background. Just taking one of those, and I can plug in on one side electric field, and if I calculate derivative of electric field with respect to time and multiply by permittivity and permeability of free space, I will get such an expression. And on the other side, I have to calculate derivative of magnetic field, which means I'm going to get expression like this. Now I have sine on this side and sine of this on this side of the same expression. So, well, if I group now, move terms from one side to the other side, well, this expression will disappear. I think in order to have peak value of electric field of a peak value of magnetic field, it means that I have to divide both sides by Bm. Then I'll get this quotient on the right hand side. And then I divide both sides by this expression, so I will get K over this product. Now, 1 over product of permeability and permittivity gives me square of the square of speed of light. Now this expression gives me inverse of speed of light, which means that ratio of electric field and magnetic field, and actually not only peak values. I can recognize that if peak values are related by that, the fields are related by the same relationship, and that they are equal to speed of light. I think I didn't write it there. Yeah, I didn't write it, but you can recognize now that 1 over permeability of free space multiply square root of product of permeability and permittivity, this quotient is speed of light. So in SI units, electric field at any point of electromagnetic wave is C times greater than magnetic field. All right. Now, when we plugged in the expressions, these cosine functions, we found that peak value, there's no limitation on peak value, and there is a relationship between angular frequency and propagation vector. But we can find a lot of them as long as the constants omega and k are selected in such a way that their quotient is equal to c. I will get a solution to the wave equation. Now, wave equation is a linear equation, so if I have two different solutions, if I combine the two solutions, that combination, if I take linear combination, then it is also going to be a solution. So actually, Maxwell's equations lead to the conclusion that electromagnetic waves are superpositions of sinusoidal waves. In other words, they are a series of trigonometric functions, which means that they are Fourier series that they are Fourier series. And well, if I think about making those combinations, I can have a wave like this. I marked only electric field vector. Remember that magnetic field vector is always perpendicular to electric field vector, following the right-hand rule. And this is the most general form of electromagnetic wave which is traveling through space. So, for example, if I think about light coming through this point, electric field at this point, due to the light which is coming from all those lamps, oscillates in a very weird way, random. It oscillates, however, in the plane perpendicular to the plane of propagation. So if I consider that light, that lamp, it means that the electric field here will oscillate like this. Now, if oscillations satisfy certain conditions, then the wave will have a particular property. For example, if oscillations are harmonic, so from that combination of trigonometric functions, there is only one trigonometric function which has coefficient non-zero. In other words, the wave is a trigonometric function. If something like this happens, we say that the wave is monochromatic. We have a certain confusion, however, confusing being monochromatic with assigning a color. It is true that monochromatic light will produce a sensation of defined color. So, for example, if the propagation vector is such that the wavelength of the wave is a little bit over, 0.55 microns, we will see it as green. If it is 0.4 microns, well, we won't see it. If it is, let's say, 0.48, it will be blue. If it is 0.7, it will be red. So a wave, a monochromatic wave, will always have a certain color. However, not every color can be observed for a monochromatic wave. Only those colors which you can see in a rainbow. So brown, for example, is not there. White is not there. And a lot of colors, more colors are actually not in the rainbow than there are in the rainbow. Now, color, however, is an attribute which we can assign to every light, and even if it is not monochromatic. But do not confuse wavelength with color. Actually, you can see colors even without light. You can, for example, close your eyes, ask your neighbor to grab physics book and hit hard on your head. You will see colors. This is why, for example, on those cartoons, usually you see those bright stars, because this is, you will see a bright color like lightning. Not mentioning, for example, that when we dream, we also see colors. And obviously it is not related to any light coming to your eye. All right, now if the oscillations follow a certain pattern, then we say that the light is polarized. So, for example, if the oscillations, if I consider this point over here, and if the light coming out from a lamp was oscillating only up and down, then we would say we would have a linearly polarized light in a vertical plane. If a light oscillates in the horizontal direction, we will have a horizontal polarization. We can also have some other types of polarization, like circular polarization. In circular polarization, if I consider this point, electric field rotates. Now I think that this would be enough for today. So thank you for your attention and see you tomorrow.